The next question is how to define properties. Well, let's look at those ones A, which we know from classical mechanics. If we have two charges, here, and one point charges, let's see, one has a charge Q and the other one has a charge minus Q. So overall the system is neutral. And they are separated by a distance r. Then standard classical, that dipole moment which we have, the dipole moment of that system of those two charges is the distance, well, never mind, the distance times the charge of those two. That is actually, I mean, that's a special case for the situation that we only have two charges. If we have a lot of charges, we have to generalize this. So for many charges, and then we also should think about that the dipole moment is a vector. So for many charges, we have a sum over all of them. What is it? M, whatever. Charge is M. And then we have the value of that charge. They don't have to be the same, obviously. And then the position vector of that charge, meaning the vector from the origin of the coordinate system which we have chosen, and that is obviously arbitrary, to where the charge is sitting. And if you only have two, then this one very easily reduces to this here. Now, we actually can, what we have in a molecule then is in a way very similar, at least when we do the Born-Oppenau approximation. I mean, the nuclei have charges, and in the Born-Oppenau approximation we hold the nuclei fixed. So for the nuclei, we are there, here. So the nuclear contribution in the Born-Oppenheimer, just solving, actually not only in the Born-Oppenheimer, but just looking at the first equation, just looking at the electronic equation, keeping the nuclei really fixed, then the nuclear contribution to a dipole moment we calculate just in this way. Because they then, if you keep them fixed, they are classical point charges. And by the way, I mean, all Schrödinger equations, we always consider nuclei as point charges. Which is not the case if you do modern relativistic quantum chemistry, then you go away from the point charge model and actually have a finite nucleus with a finite size. But what do we do about the electrons? Because the electrons are not localized at a particular point. What do we do if we have not fixed charges, but we sort of have a charge distribution? So if we have not individual ones, but some kind of a charge distribution, which we can describe by charge density, which depends then on position in space, and for every point we have potentially a different value. So this is for discrete charges, and this is sort of for continuous charge distribution. So what happens to that expression then, if we go to a continuous charge distribution? What happens to a summation if you have very many points.
Converts to integral.
Yes, that turns into an integral. So instead of summing over all the individual charges, we just integrate over the charge distribution now. And then times the position. So instead of having the sum over Q, we have now the integral of the charge distribution, dr. And that is still classical. I mean, there's just, this is discrete charges, a continuous charge distribution. But when we then later go to the quantum mechanics, as I said, we can use this for the nuclei. And this describes the situation of the electrons. So if we, in some way or another, can calculate the charge distribution of the electrons, we can actually use that expression directly. Well, another property is the quadrupole moment. Story is very much the same. The integral looks a bit different then. A quadrupole moment is a tensor. This is a vector. Quadrupole moment is a tensor which has, in principle, 9 elements. In practice, actually, it only has 5 unique elements. And that is, again, it's an integral over the charge distribution, and then it's R vector times R vector transposed, which then here gives me the tensor.